Hello, and welcome to my 2019 GYPT presentation about problem number 5, filling up a bottle. My name is Timo Huber, I'm from Berlin, and part of the team Wir hätten lieber ausgeschlafen. So the task, as stated by GYPT, was as follows. When a vertical water jet enters a bottle, sound may be produced, and as the bottle is filled up, the properties of the sound change. So there are three interesting aspects about this task. First, that sound may be produced. We're going to talk about when is sound actually being produced. Then the properties of the sound and how these properties change. And then the question is how relevant parameters affect the system. So we're going to start off with a quick demonstration. We've all done this before. We're on our way to school, to work, we're taking our bottle and putting it under the tap. Filling it up produces a sound, which sounds like so. And that's the sound we will be talking about today. So this is the experimental setup that I investigated the sound with. We have some sort of nozzle where water is pumped through with a constant volumetric flow rate, producing a jet, dropping in some sort of bottle model. So for sakes of simplicity, I've used perfect cylinders as bottles at first. We're going to talk about that model later on. But nevertheless, we recorded the sound, of course, with a microphone and analyzed the spectrum using Audacity and Vista Video Pro, and we filmed the container to keep track of the water height and analyze it using VianaNet. So let's first talk about some dimensions or properties of our setup. So we have some sort of container and a nozzle, which have a distance from each other, which I'll refer to as h index n. The container or the bottle has certain dimensions, a height and a diameter, and due to a constant volumetric flow rate and the gravitational acceleration downward or in z direction, we have a jet with certain properties such as the nozzle radius and the speed at the nozzle, and of course the flow rate. The water being used has certain properties which change with temperature, the density, the surface tension, the dynamic viscosity, and the air surrounding the experiment, of course, also has certain properties, most importantly, the speed of sound and the changing of these properties with temperature. So when the jet fills up the container, we have a water height and a cavity height. A cavity height from the water surface to the top of the bottle, and we have a drop height that the jet needs to drop to splash into the water container. So these three dimensions change over time. So to understand the phenomenon, we first have to talk about standing waves. Standing waves occur in this container, which I have flipped to the side for demonstration purposes, with a closed and an open end. So in this cavity height, we have a ground frequency and different harmonics, and the wavelength of these standing waves is of course related to the cavity height, and with the speed of sound, we can calculate the frequencies that these standing waves oscillate at. And these, of course, change with a changing cavity height. So the first interesting observation is that not the amount of water already being filled up into the bottle is important, but the height or the cavity over the water surface. So as mentioned before, I kept track of the water height over time, and due to the constant volumetric flow rate and the cylindrical form of our bottle, we can fit this linearly. And with an increasing water height, of course, we have a decreasing cavity height, and this cavity height can be plugged into our formula for the frequencies. And when we plot these frequencies for a certain experimental setup with certain dimensions, we get these results. So these are the frequencies that the experiment should reveal, so a ground frequency and 3 harmonics. And when we analyze the sound that we recorded with a spectrum analyzer, so it's a frequency on the y-axis, time on the x-axis, and of course the amplitude of a certain frequency at a certain time on the z-axis presented as color, we see that our experimental data matches the calculations quite well. So we have the rising fundamental frequency and some harmonics and background noise. So we've derived a mathematical model revealing accurate predictions for the frequency. Another thing that we have realized is that the amplitudes decrease with increasing frequency, and to understand that, we have to look at water jet and water surface interactions. So these are two types of water jet hitting a water surface. On the left, we see nearly laminar flow, not split up into droplets hitting a water surface, plugging very little bubbles underwater. And on the right side, we see a jet which has already split up into droplets, plugging a lot of water bubbles under the water surface. So one thing that we realized is that when we have bubbles inside the water, we hear a sound, whereas when we don't have any bubbles inside the water, we don't hear any sound. So we have to understand, how do the bubbles get into water? This is due to the jet being split up into droplets, as we saw on the right there, and this phenomenon can basically be explained by the water jet being constantly accelerated downwards. So with an increasing velocity due to the constant flow rate, we have a decreasing water radius, and this water jet has a wave of perturbations propagating along it, and this certain wavelength, when it has a certain relation to the water jet radius, the water jet splits up into droplets like so. This looks a little bit like this. This happens at a constant height, the plateau Rayleigh height, I'll call it for now. And it looks like this. We have a constant jet splitting up into droplets, which then produce the sound inside the water. So let's look at the bubbles. On the left, you can see a bubble which is being plugged underwater by an incoming droplet, and we see that it oscillates at a certain frequency known as the Minyard frequency, and the oscillation of this bubble can be derived or is proportional to 1 over the bubble radius and can be calculated by this formula. So when we look at the bubble diameters, we can determine what bubble sounds or what bubble frequencies are being produced. So we can see we have a certain distribution right there, and the bubble sizes are organized nicely. We have not as many large bubbles as we have small bubbles, but if we generate a spectrum with a formula introduced by Kees van den Doel in 2004, we can see that the lower frequencies have a much higher amplitude than the higher frequencies, because a large bubble obviously displaces more water, and this affects the amplitude. So this explains the decreasing amplitude from the low frequencies to the high frequencies. But another thing that we have noticed is that we only hear the high frequencies in the beginning, and the lower, louder frequencies become audible a little bit later. And this can be explained with a phenomenon known as the hydraulic jump. We can all observe this in our kitchen sink at home. A water jet hits a surface, and on this surface there is a circular hydraulic jump due to sub and supercritical flow. This radius is constant when the water flows away in the kitchen sink, but if we put it into a container, or if we let a jet splash into a container, we see that this radius decreases over time due to the rising water level. And when the water level is rising, only then we have enough room for large enough bubbles to oscillate under the water surface. So only when the radius has reached 0, we hear the very large bubbles underwater. So that's why we hear the low frequencies later than the high frequencies. So let's talk about the model we've used to analyze this So let's talk about the model that we've used to analyze this phenomenon at first. So we've used perfect cylinders, but that is of course not accurate at all for every bottle. So we can model the bottle as some sort of function wrapped around an axis as a solid of rotation. And it's obvious that at a wider point, the water height changes more slowly than at a more narrow point. For example, here, the change of the water height is much smaller than it is here. So when we plug this into our cavity height formula, we know that we can calculate the cavity for every container for every given moment in time, and plug this into our frequency and get the exact frequencies at every moment in time. So this new model brings up another question. What about resonances inside the bottle? How does the shape of the bottle affect this problem. So we can observe this or answer this question by conducting a simple experiment. Does the green container produce the same frequencies as this blue container? And if we do that and measure the data, we see that on the left side, or in the lower frequency spectrum, we have different peaks, whereas we have almost the same peak at around 1100 Hertz. And this can be explained with a model known as a Helmholtz resonator. And this Helmholtz resonance assumes that the air inside the bottle is compressible and lets the air in the bottle neck oscillate, such as a simple oscillator with a spring and a mass. And this Helmholtz resonance can be calculated by this formula with the speed of sound, the area of the opening, the volume of air inside the bottle, and the length of the neck. And if we plug in the dimensions of our experimental setup into the formula up there, we can calculate the different frequencies and harmonics. And when we look at the plot, we see that we hit two of these harmonics with our peaks, and we see that this model is valid. So if we look at the normal cylinder from the beginning, we see that our other method also holds to calculate the peaks that occur in this experiment, and we see that the blue plot has also reached a peak at the first harmonic over there, so both models are valid. So in conclusion, we can say that the oscillation of the different bubble radii determine their frequencies, and the larger bubbles with the lower frequencies are much louder. And by modeling our bottle as a solid of rotation, we can predict the water height for every moment in time. And with the Helmholtz resonance and standing wave model, we can then predict the frequencies for every moment in time and calculate these diagrams, which perfectly match our experimental data. Thank you for your attention.